Hi, I'm Mark Barsamian. In this video, I'll be discussing graphing. This material is from section 4.2, Second Derivatives and Graphs. And more specifically, it's from sort of the middle of the section, 263 to 267. These three examples, 4, 5, and 6 in the book, are similar to some things that we do in this video. The corresponding homework is this collection of 4 exercises from section 4.2. Going to start by recalling some concepts from sections 4.1 and 4.2 that we've discussed in previous videos. And in the videos for section 4.1, we discussed these correspondences between the sign behavior of f prime of x at a particular x value and the corresponding behavior of the graph of f of x at x equals c. That is, the sign of f prime of x at a particular x value tells us whether the line that's tangent to the graph of f of x at x equals c tilts upward or tilts downward or is horizontal. And we discussed the correspondence between the sign behavior of f prime on a whole interval and the corresponding behavior of the graph of f on that same interval. The correspondence is the sign behavior of f prime on an interval tells us whether f of x is increasing or decreasing or constant on that interval. And we had the idea of a local max and a local min. A local max is a y value that's the greatest y value on an interval. And the local min is a y value that's the least y value on an interval. And we had the procedure called the first derivative test for finding local extrema. Basically, you look for places on the sign chart for f prime of x where f prime changes from positive to negative or negative to positive. In section 4.2, we discussed the second derivative, and we discussed the correspondence between the sign behavior of f double prime and the concavity behavior of f of x. So the correspondence is that if f double prime is positive on an interval, that tells us that f prime is increasing on that interval, which in turn means that f of x is concave up on that interval. And similarly for f double prime being negative and f being concave down. Remember what the definition of concavity was. The words f is concave up on an interval refer to graphs that look like this. Graph has a tangent line at each point in the interval, and if you look at any one of those tangent lines and you look at the graph and the tangent line for x values near that point of tangency, the graph is above the tangent line. What I want to talk about in this video is this idea that these correspondences between the sign behavior of f prime and the increasing decreasing behavior of f, and the correspondences between the sign behavior of f double prime and the concavity behavior of f, those correspondences can be used to come up with a strategy for graphing a function that's given by a formula. The graphing strategy is 4 steps. The first 3 steps are analyzing f prime, and analyzing f double prime. Now, the procedure that's presented in the book is fairly wordy, but the idea is that you ask the easy questions about each of these functions. About f of x, you ask about the domain and the axis intercepts. The x-intercepts on a graph are solutions of this equation. You set y equal to 0 and solve for x. The x-intercepts on a graph are obtained by doing this. Set x equal to 0 and solve for y. Notice that both of those things, finding x-intercepts and y-intercepts, involve 0. To find x-intercepts, again, you set y equal to 0 and solve for x. To find the y-intercept, you set x equal to 0 and you find y. We'll also be talking about analyzing the function f of x just to determine whether the y values are positive or negative, that is, whether they're greater than 0 or less than 0. Then we'll turn our attention to analyzing f prime. And so the idea of this is that you find the sign behavior of f prime and you use that to find out information about f. Where is f increasing and decreasing, and where does f have local extrema? Then you turn your attention to f double prime. You analyze f double prime by making a sign chart for f double prime. So you study the sign behavior of f double prime, and that tells you about the intervals where f is concave up and concave down, and it helps you find the inflection points of the function f. Then with all that information that you've gathered in steps 1, 2, and 3, you sketch the graph of the function. Our first example involves given information about a function where basically parts of steps 1, 2, and 3 have already been done. Remember those steps. Step 1, you analyze f. Step 2, you analyze f prime. Step 3, analyze f double prime. Parts of the analysis of f prime involve making a sign chart for f prime. Parts of the analysis for f double prime is making a sign chart for f double prime. Well, in this first example, we're given information that is the sign chart for f prime and also the sign chart for f double prime. And we're supposed to sketch a possible graph of f of x. Well, how do we proceed? The first thing we should do is we should translate the given information about the sign behavior of f prime into information about the behavior of f. So these intervals where f prime is negative will be intervals where f is decreasing. That interval where f prime is positive will be an interval where f is increasing. And these x values where f prime is 0 will be places where f has a horizontal tangent line. So let's write that information on this number line. Notice that when I added my notes to the sign chart, I made sure to put f next to each of them. F is decreasing, f is horizontal, f is decreasing, and so forth. The given sign chart I made with f prime labeling all the information about f prime. It's very dangerous to put information about f and f prime together on one chart because it's possible to confuse the idea of increasing and the idea of positive. I've talked about that in previous videos. We have to be very clear. F prime is the thing that's positive. F is the thing that's increasing. All right, so we've translated this given information about f prime, about the sign of f prime, into corresponding information about f. Let's do the same thing for this given information about the sign of f double prime. All right, so there is all the information given about the sign behavior of f double prime translated into information about f. Now let's make a graph. We'll make the graph on the next page. So there are my coordinate axes. Now let's go back up and look at our given information. We have this information about x, y coordinates of points on the graph. When x is 5, y is 12. When x is 10, y is 8. When x is 15, y is 4. So we can plot those 3 points. Notice if that were all the information we had about the function, then the graph that we would guess would just be a line that connects these 3 points. That would be our simplest way of guessing what the graph of f looks like. But those 3 points are not our only information. Now we have to add this information. F decreasing, then horizontal, then decreasing, then horizontal, then increasing. So there I've used symbols for f being decreasing or horizontal or increasing on this row, arrows slanting down or slanting up, and red horizontal tangent lines. And then on this row, I've used symbols denoting f being concave down or concave up, and then little x's for the places where there are to be inflection points. Well, let's start by putting the horizontal tangent line markings and the inflection point markings on the points that we've already plotted. So we have to have a graph that goes through those points with horizontal tangent lines at those two locations and inflection points at these two locations, and with this increasing, decreasing, and concavity behavior in each of those intervals in between. So we need to have a graph that's decreasing and concave up and arrives at that point horizontally. And then in the next interval, the graph needs to be decreasing and concave down, needs to start out from this point horizontally, but it doesn't arrive at the next point horizontally. It arrives still decreasing. The next interval, the graph has to be decreasing and concave up, has to start being decreasing and arrive at the next point being horizontal. On the final interval, the graph needs to be increasing concave up, needs to start horizontal. So there's an example of a graph that does all that stuff. Let's go on. Example 2. In this example, we're given a bunch of information about points on the graph of f and sign behavior of f prime and sign behavior of f double prime, but the sign behavior of f prime and f double prime is not given in the form of sign charts. It's given in the form of inequalities on certain intervals. We're supposed to sketch a possible graph of f of x. Well, it's the same idea. We'll start by translating this given information about the sign behavior of f prime and f double prime into information about f. And then we'll collect all that information that we've got about f and we'll put it on some coordinate axes and we'll draw a graph that it describes. So let's start by translating the given information about the sign of f prime into information about f. All right, there's our information about the sign behavior of f prime and f double prime translated into information about f. Now our job is to take all this information about f that we've got, all that information, put it on a set of axes, and try to sketch a graph that follows that prescription. All right, we start by plotting the points that we were given. -2, -2, 0, 1, and 2, 4. So there are our 3 points. Now again, as I said in the previous example, if this is all we knew about our function and we were told to graph, we would just guess, well, the graph is just going to connect these points. But we have other information that we've been given from the given information about the sign of f prime and the sign of f double prime. Let's bring that information down here. So I'm going to copy all this stuff and bring it down. So I'm going to divide the domain up into regions between these x values where we have these given points. And on each of these intervals, I'm going to put the given information. Now, it looks like I've made a mistake here. Notice that my function changes concavity at x equals 0. So the inflection point should be at x equals 0. So on the previous page, I'll change that as well. So there I've indicated the inflection point at x equals 0 by putting a little x on the graph. All right, there's the information that we were given on the previous page. Now that I've got all that stuff put on the axes, I'm going to get rid of these sentences. And we're ready to draw our graph. Now notice the mistake that I made earlier. This red horizontal tangent line should be at the point that we knew was going to be on the graph. And there's the graph of our function. Now we can clean it up by getting rid of a bunch of the marks. And there's our cleaned up graph. Let's go on. Example 3, this is similar to 4.2, number 56. F of x in this problem is given by a formula, and we're supposed to use the graphing strategy to graph f of x. Well, let's go back up and recall the graphing strategy. Remember, the graphing strategy is analyze f by asking the simple questions about f, the domain, the axis intercepts, where it's positive and negative, and then analyze f prime, finding its sign behavior, and then using that to make conclusions about f, and then analyze f double prime, finding its sign behavior, and using that to make conclusions about f. So let's start with step 1. Okay, the easy questions about f. First of all, is domain. Well, f is a polynomial, so its domain is all real numbers. What about the axis intercepts? Find the y-intercept by setting x equal to 0 and solving for y. Okay, now we find the x-intercepts by setting y equal to 0 and solving for x. So we found the x-intercepts by setting y equal to 0 and solving for x. Now that involved this difficult factoring, which I did in advance. I arrived at this factored form. Now you don't have to, in any of your homework, have to factor something this complicated. But factoring is something that you've learned about in previous courses, so this is something that should not be foreign to you. Certainly with some work you can figure out how to do this kind of factorization. The main thing is you could check this by multiplying all these factors together, and you would figure out that you really do get that. And look what it tells us. It tells us that these are the x-intercepts, those 2 points. Those x values correspond to the solutions to these two linear terms. The term x plus 3 corresponds to the x-intercept at negative 3, 0. The term x minus 3 corresponds to the x-intercept at 3, 0. This term is an irreducible quadratic form. There are no x values that cause that term to be 0. Now, there's a little bit more that I want to say about analyzing f of x. So we have answered some of the easiest questions we could. We figured out the domain of f, that was easy. We found the y-intercept, that was very simple. We found the x-intercepts, which was conceptually simple. It did require this one factoring, which was hard. There is one more bit of information that I want to think about, and that is the end behavior. Without doing any work, we can look at that function and think about how the shape of the graph will look, and in particular the ends of the graph. Notice that that's an even degree polynomial with an odd leading coefficient. So that means that both ends of the graph go down. So again, that's an easy question to ask. We don't have to do any calculations. We just scrutinize the leading term. Now, the fact that both ends of the graph go down and the graph only touches the x-axis at these 2 points can be used to say something about where the graph is above the axis and where the graph is below the axis. Now I'm going to need a little bit more space, but I'd like to do that on this page, so I'm going to shrink all the stuff that we've written so far. So if we think about the graph of f, we know that the ends have to go down and the graph has to go through those 2 red x-intercepts. We also know that the graph has to go through that y-intercept. So the graph can only touch the axis at those two red points. The ends have to be down below the axis, and the middle has to be above the axis apparently, because it's got to go through that point. So that tells us that our graph has to have that behavior. The y values have to be negative and going down on the left side. They have to be above the axis in the middle in order to go through that red y-intercept. And the graph has to be negative again below the axis in order to go down on the right side. So all of that stuff was determined in step 1, analyzing the function f of x, not doing terribly difficult computations, except for this one factoring step, which I did. Okay, now let's go on and do step 2. Remember what happens in step 2. In step 2, we analyze f prime. We make a sign chart for f prime, and we use it to get information about the increasing, decreasing behavior of f. So there's our function. F of x is minus x to the fourth plus 6x squared plus 27. So we need to find its derivative. Now, this factorization might seem kind of tricky. I factored this x squared minus 3 as x plus square root of 3, x minus square root of 3. That comes from the idea of the difference between two squares. So we know that the difference of two squares factors this way. A squared minus b squared equals a plus b times a minus b. Well, I could think of that as the square of x. So there is my x. And I could think of this as the square of the square root of 3. Now, I'm going to rewrite this factorization in a different order, because I want to have the factors in the same order as the corresponding partition numbers. So we get these three partition numbers. This partition number corresponds to that factor. This partition number corresponds to that factor. And this partition number corresponds to that factor. Now we need to make a sign chart for f prime. So there's our sign chart for f prime with the behavior at the partition numbers indicated. Now we need to find test numbers. Remember that square root of 3 is about 1.7, so I've chosen test numbers to the side of that. Now we have to find the sign of f prime at each of these test numbers. Now for my sign calculations, I can choose which form of f prime to use. I could use the standard form, or I could use the factored form. Actually, what's going to turn out to be the most convenient form to use is this sort of halfway factored form. So there are our sign calculations. So we put that on the sign chart. So there is our sign information put on the sign chart. Now, what are we supposed to do with this? Well, we're supposed to figure out what it tells us about where f is increasing and decreasing and where f has local extrema. We'll do that on the next page. All right, there is the information about f that we can glean from the sign chart for f prime. I've been sure to say that f is increasing because f prime is positive. I've given reasons. F is decreasing because f prime is negative. And I've said that f has a local max at the x coordinates that we know because, why? Because f prime changes from positive to 0 to negative. Now there's one last thing to do, that is to find the y-coordinates of the extrema. So in computing f of negative square root of 3, we arrive at this calculation, which looks kind of scary. But let's look at this one. The negative square root of 3 squared is just 3. So this is going to be 6 times 3. Now, negative square root of 3 raised to the 4th power is just negative square root of 3 squared and then squared again. So that's just going to be 3 squared. That's going to be 9. So there, when you plug in the x values and find the corresponding y values, we find the y values are 36 and 27 and 36 at those 3 x values. So that tells us that the xy coordinates of our extrema points are negative square root of 3, 36, plus square root of 3, 36, and 0, 27. Okay, so that's the end of our analysis of f prime. That's the end of step 2. So now in step 3, what do? Let's go back up and look. So we finished step 2. We analyzed f prime. We made a sign chart for f prime, and we found the intervals where f was increasing or decreasing. We found the local extrema. Now we have to find f double prime, make a sign chart for f double prime, and use it to get information about f. So f prime is this, minus 4x cubed plus 12x. So we have to find the derivative of that to get f double prime. So there's f double prime. Now we can see that it factors easily, so we can find the partition numbers for f double prime are x equals -1 and x equals 1. So let's make a sign chart for f double prime. We have to find the sign of f double prime of -2. We could either use the standard form of f double prime, or the factored form of f double prime, or this. Let's use this one. So there's our sign information about f double prime put onto the sign chart for f double prime. Now let's use this to make conclusions about the behavior of f. So we find that f is concave up in this middle interval where f double prime is positive, and f is concave down on these intervals where f double prime is negative. Now that tells us that there are inflection points here at those 2 x values. So let's write that on the next page, and we'll need to find the y coordinates of those inflection points. So there are the y coordinates. Notice I used the formula for f of x. We have to find y coordinates on the graph of f of x. So we use the formula for f of x, not the formula for f prime, not the formula for f double prime. So the xy coordinates of the inflection points All right, that's the end of our analysis for step 2. Again, remember what we did. We found f double prime. We made a sign chart for f double prime, and we used the sign information about f double prime to get information about f. So we did this. So we've done step 1, analyzing f. We've done step 2, analyzing f prime, and step 3, analyzing f double prime. Step 4, we take all that information that we got in those previous 3 steps, we put all that information together on axes and use that information to sketch a graph. So in step 1, we got this information, so we'll be sure to put that on the axes. In step 2, we found this information, the local maxes and local mins at those coordinates. So we'll be sure to put those local maxes and mins on the axes, and we'll note the increasing, decreasing behavior. And then in step 3, we found these inflection points, and we have the concavity behavior on the intervals between those inflection points. So we'll put all that stuff on the axes. All right, so the information from step 1, the x-intercepts and the y-intercept, and the fact that the graph goes down on the ends and is positive in the middle or above the axis. All right, in step 2, we found these local extrema. And then in step 3, we found inflection points. Now we can add to this graph the increasing, decreasing behavior and the concavity behavior. I think it's actually clearest if we just add the concavity behavior. We have to have a graph that has that concavity behavior, and I think you'll see that the increasing, decreasing behavior will match what we found in step 2. So there you go. There's a graph that matches that concavity behavior, and I think you see that it matches the increasing, decreasing behavior as well. It is increasing until you get to negative square root of 3, decreasing until you get to x equals 0, increasing again until you get to positive square root of 3, and then decreasing to the right of that. And you can see that both ends of the graph go down. All right, that's a very long example, but it's a good example of the use of the graphing strategy. Let's go on. The last example for today is revisiting an example from 2 earlier videos. It's similar to 4.2 number 77. In this example, the graph of f prime is shown at right. So not f of x, this is f prime of x. The goal is to come up with a graph of f of x. We'll do that on the next page. But what we'll do in order to do that is we're going to scrutinize behavior of f prime in order to get conclusions about the behavior of f of x. Now, what sorts of things will we look at? Well, let's go back to the very beginning of this video. Remember that information about f prime being positive or negative translates into information about f being increasing or decreasing. So we want to look at f prime, look at that graph, and scrutinize its positive and negative behavior. Also, notice that when f prime is increasing, that corresponds to f being concave up. And when f prime is decreasing, that corresponds to f being concave down. So we want to also scrutinize f prime's graph to think about where f prime is increasing or decreasing. So in these cells, we're going to be scrutinizing this given graph of f prime to figure out where it's positive and negative and 0. And in these cells, we're going to be scrutinizing the given graph of f prime to figure out where it's increasing or decreasing. Notice, first of all, at these 2 points, x equals negative 3 and x equals 4, f prime is 0. And notice that on this region of the graph and on this region of the graph of f prime is above the axis. So that means f prime is positive. And in this region of the graph, to the right of 4, the graph of f prime is below the axis. So f prime is negative. Now what about the increasing, decreasing behavior of f prime? Well, notice, first of all, that at these 2 x values, f prime has a horizontal tangent. So at x equals negative 3 and at x equals 1. Now notice that In this portion of the graph, between x equals -3 and x equals 1, f prime is increasing. So that is there. Circle that, increasing. Notice this portion of the graph and this portion of the graph, f prime is on its way down, so f prime is decreasing. Now let's translate all that information about f prime and into information about f. So the fact that f prime is positive means that the positive, negative, and zero behavior of f prime translates into increasing, decreasing, and horizontal behavior of f. Now let's translate all this information about the increasing, decreasing behavior of f prime and what it tells us about f. So there's our conclusions about the behavior of f. Now let's, on the next page, draw a graph. So first of all, we'll notice that at x equals -3 and at x equals 4, f will have horizontal tangents. So I'll put a guideline in for that. Now let's go back up and look at more information. We know that f is increasing in these intervals and then decreasing in the far right interval. Let's go back up. F has inflection points at x equals -3 and at x equals 1. So let's put those on the graph. And then f has to alternate being concave down, concave up, then concave down. Okay, we need to sketch a graph that does all of those things. Here's one attempt. Have to be increasing concave down, then switch to increasing concave up, then switch to increasing concave down, and then switch to decreasing concave down. There's a graph of our function. Let's get rid of all the other junk. Well, actually, no, we can just leave all that. That's the end of this example, and that's the end of the video.